Yeah, my screen is visible. Yeah. Okay. So a simple semigroup with zero minimal left and right ideas, meaning that we must have minimum ideas apart from the zero. Okay, then those are called zero minimal right and left ideas, and semigroup which has zero minimal right and left ideas are called zero completely simple. That's just an adjustment that we have to make when we have a zero, and so we don't want that to be the minimal only. Right. Okay, so now since our definitions are in terms of minimal left and right ideas, we should try to see some correspondence between that and the objects that we have already studied, that is L classes and so on. Okay, so the claim is that if you have a zero minimal left ideal, okay, then it is actually an L class. It's actually an L class, and so if it's an L class, it will be a minimal L class, and also every minimal L class, since it's minimal, it will have to be an ideal. Okay, but we can just run the proof. It's simple. So basically you start with an x in your zero minimal left ideal, and let's say there is some other y which is a part of the L class. So then there is a t. It means that x multiplied with t on the right gives you the y. Okay. But Tx must be in L because it's an ideal. So obviously it contains L classes. I mean, potentially it contains, every ideal will obviously contain the L classes, but now we want to show that it's exactly an L class. Okay. So now let's say two things are in L, are in this ideal. We want to show that they are L related. Okay. So they obviously produce the same left ideal. Okay, because you cannot produce anything smaller than that left ideal. So they produce L. Okay, which means that y belongs to Sx and x belongs to Sy, which exactly means that they are L related. So exactly these are the corresponding. This will be useful because your L classes, because zero minimal left ideas are becoming L classes. It will be useful because we'll see in completely simple semigroups, every L class will be minimal, and so they will also become left ideals. Okay, so that's the other direction which I've not explicitly shown, but that is also true. It's just simple to check. So every minimal L class will become left ideal, and that will be useful to us. So right, and obviously this L class that we have is obviously minimal, so that's fine. Yeah, now minimal L class is a left ideal because, yeah, so I was just saying this is the obvious part from right to left, because I mean you simply cannot go down when you multiply by when you multiply on the left, you have to stay in that L class because you cannot go down, so it just becomes an ideal, a left ideal, I mean, yeah, and it's minimal. Yeah. And similarly we have the other analogous result. If you have a zero minimal right ideal, then they become zero minimal R classes, and zero minimal ideals become minimal J classes. Okay, so minimality makes classes ideals. Maybe you can just remember that. Right. So this leads us to the following conclusion. Let's see. So if M is a finite, so here we need the finiteness condition, is a finite zero minimal ideal. So L itself is a, M itself is a finite zero minimal ideal. So it's a semigroup, but at the same time, it's just a, or we can just say it's a finite zero minimal ideal. Okay. Then all the L classes of M are minimal. So M is just the D class. Okay, M is just a D class, and so all the L classes inside that will be incomparable, and so they will all have to be minimal in the finite case. And we know, yeah, this will be true in the finite case. Okay. Yeah. So the explanation is M is a D class because it's an ideal and it's finite, so it's a D class. And so we know that two elements are, I mean, two elements means if you take two elements, either they're in the same L class, or if they're in different L classes, then they have to be incomparable, because we have seen this. Two things which are in the same D class, or any two L classes in the same D class are incomparable. So I've probably repeated myself. Right. And now this is the interesting thing, that this is also true in the infinite case, provided we assume that M has at least one minimal left ideal to start with. Okay, so we'll prove this. Okay. And so this is again rehashing my point that just adding a condition of having minimal left ideals, or adding this condition of completely simple, extends the result which was obvious in the finite case to the infinite case. So the proof is slightly different. Yeah. So formally this is the statement. Okay. So M, if M, so this is again, this is a good result to have. This will help us to show that every L class in a completely simple semigroup is minimal, and so it's an ideal. Every L class becomes an ideal, okay? A left ideal, and so on. So this is a formally, this is the result. If M is a zero minimal ideal, okay, maybe infinite, and has at least one minimal left ideal to start with. Otherwise, this may not be true. And all the L classes of M are minimal. Okay? All the L classes of M are minimal. In other words, this is the form in which we'll prove it, is that M is a union. M is the union of all the left ideals of S in M. Okay? So this is the form in which we'll try to prove it. Okay? So M is the union of all the left ideals of S that is in M. Yeah. So what is the idea of this proof? So we'll prove it based on like properties and so on. So we will take the union of all the left ideals in M. Okay, we just take the set theoretic union. Yeah, we call it a set and so on, and show that this itself is a two-sided ideal. Now this, why will be done? Because the minimality of M will be done if we can show this. So that's what we'll do next. So yeah. So let I be the union. So let I be the union of all the left ideals in M. Okay, the claim is this is the two-sided ideal. So this is the way in which we are proving. We're not showing that this is everything directly. We'll just show this is a two-sided ideal. Okay. So see, it's already a left ideal. There is no question about that. It's a union of left ideals is a left ideal. There is no other addition structure to worry about. So it's a left ideal. Now, so we want to show it's a right ideal as well, right? So you take an A in I and an S in S. So we have to show for all S. So take an S in S, and the goal is to show that A times S is in I again. Right? We want to show that A times S is in I again. Yeah. So basically, we want to show that A times S is in some other left ideal. Right? That's what I is made up of, right? So we will want to maybe cook up a left ideal in M which contains S. That will be enough. That's what I is. So what do? We just we take L times S. Okay, so what is this L? Sorry. So this L is the left ideal that contains A. So remember, A is in I. So A is in a left ideal, right? So A is inside L, right? So that is the L that this is. Okay. So we take L times S. That seems like a good choice, right? So this is the thing, and this is the left ideal, right? And we want to show that AS. Wait a minute. Yeah, we want to show that AS is in LS. Yeah, LS is a left ideal, but the only thing we don't know is whether it's minimal or not. That is a problem, right? So we want to show whether it's minimal or not. So yeah, we need to show that it's minimal. Yeah. So let's see what we do next. So we need to show that LS is minimal. Okay. Yeah. So is it enough to show that it is minimal? Right. Yeah. Right. Okay. Okay. So then, I mean, so if it is not, we just go by the usual contradiction way. You take a B which is inside LS, and then you basically take the part of the part of B which is inside LS, and that is A. Okay. So A is you take X in L, which such that X is in B. Okay. So again, A is also a left ideal because L is a left ideal. So A is a left ideal, and A is a left ideal in L. Okay. A is a left ideal in L. So because L is minimal, okay, because L is minimal, all right. So I was a union of all the minimal left ideals. Yeah. I think that's the problem in this statement. I will be the union of all the minimal left ideals, and we'll show that this is M. That's right. We want to show that I is a union of all minimal left ideals. Sorry, that's a mistake here. Okay. So I is a union of all minimal left ideals, and here M will be the union of all minimal left ideals. Right. So yeah, that's the way. That's why we have this A equal to L. Okay, A equal to L, and which means AS equal to LS, and this is just some basic thing which you can check. So A times S. Basically, yeah, you can conclude from here that LS is equal to B. Okay? So yeah, LS is equal to B, and that means okay. So one second. So LS is equal to B, which means that all three are equal, right? Which means that LS is equal to AS and so on. Yeah. So A is equal to L, and so A times S is equal to L times S, and A times S is inside B, right? And LS is equal to B, right? Yeah. So so LS is minimal. That's what we wanted to show, right? And so I is a right ideal, right? Yeah. So one second. So A is a left ideal in L, right? So A is equal to L, that's clear. And because A is equal to L, AS is equal to LS, but A times S will be contained in B because obviously that's why we are constructing the A. Okay. Yeah, so which means that LS is equal to B. Yeah, but we had that B is contained in LS. Right, yeah, so LS is, sorry, so B, we assume that there is a B, sorry, I'm sorry. So B is a left ideal which is contained in LS, but then it's not actually contained because it's equal. Sorry, so LS is minimal. Yeah, yeah, sorry. Right, so we have proved the statement that if M is a zero minimal ideal, then it's a union of all its minimal left ideals. So that's minimal condition has to be there. Okay? So which means that all the L classes are left ideals and all right classes are right ideals and so on. So that will be useful. Right. So now we want to prove some small lemmas again for minimal ideals, okay? Because this hold for minimal ideals. So just prove it here. Right. So the idea is that when you have a zero minimal ideal, okay, if you have a zero minimal ideal, it basically means that there is no ideal inside that, right? So if you take so if you start with an element which is not zero and you take the two-sided ideal of that, it could either be M or it could be zero. It could be zero also. Okay. But we are claiming that it will never be, so we are claiming that if there is an A for which MAM is not is zero, okay, if there is a non-zero A for which it is zero, then M square itself is zero, which means that for all A it will be, okay. So either M square is zero or there is an or so either M square is zero, which means there is no A, it's completely null, or for all A it is M. Okay, so never zero. Okay, so here we are not assuming that M has identity or anything like that. Okay, but it still holds. Okay, so what happens to one element kind of happens to every element. That's the interesting thing. Yeah. So again, the proof is simple. Let's just see the proof here. Okay, so of course we have to assume that this is not true for some. We want to assume that this statement is not true for some A. M is not M for some A. So let's say for some A it is zero. So now you already have something to start with. So you take the collection of all X for which it is zero, and you see that this is an ideal, because I mean if M is zero, then U X V, and if you multiply M on both sides, that would also be zero, right? Yeah. So that means, so now X is a non-trivial ideal, but because of the minimality, X is equal to M, right? Which means that MXM, M capital X M, that is M cube is zero, but right, the M cube is zero. But now we want to what is our goal? We want to show M square is zero, right? So we know that M square is a two-sided ideal. So again, M square is M or it is zero. So since M cube is zero, M square has to be zero, because if M square is M, then M cube is M, and so on, so on. So yeah, so we have shown that these are the only two possibilities. So there's nothing in the middle. That's for some elements it could be the ideal could be zero. For some it could be M. No, it's either always M or either always zero. Right. So now we have developed some theorems to prove this is one of the main results for completely simple semigroups before we go to the represent like the matrix theorem for completely simple semigroups. Yeah. And then from there we can go to the applying it in transformation semigroups. Okay. So so first of all, if S is a completely simple semigroup, meaning simple semigroup which has zero minimal left ideals and zero minimal right ideals, at least one to start with. Okay. Then the claim is that S is a union of all zero minimal left ideals. Okay. I mean, this is something which you all just showed, right? Yeah. So that's right. Right. And now the second thing is important. So second thing is important that R intersection L for every, so now we are tending towards trying to prove that completely zero simple semigroup. So this is the idea. We are tending towards trying to prove that a completely zero simple semigroup will be not just a J class. Okay, it's certainly a J class because it's simple, but it's also a D class. Okay, so that's what we are trying to tend towards. Right? So this is in that we're trying to show this, that intersection of every R and left, I mean every R class and left R class and left class intersection is non-empty. Okay, so we are showing that for ideals, but we know they are the same things in this group. I mean, you have just to add a zero to the R class to get the ideal, and remove a zero and get the R class. Right. So we want to show that for every zero minimal left ideal, left and right ideas, the intersection is non-zero, and that makes it a D class. Okay, which is again, kind of what happens in finite semigroups. J classes become D classes, but here it's infinite potentially. Okay. Now, how do we prove it? The proof is again very simple. It's a very simple proof. So R intersection L, again, you just want to show there's something in it. So I mean, just take the obvious things. So um, first of all, how will they look like? Because they are minimal, they will be principal. And so we have this, right? R is like this and S is S times B. And so if you want an intersection, I mean, A, S, B is obviously your natural choice. And then again, you can do this simple check and show that it is non-empty. And you want to show that A, S, B is certainly contained in R intersection L, but you want to show that it's non-empty. That you can again simply check using the previous lemma. Okay. So that I'm skipping that proof. Right. Okay. So now we know that it's a D class. So I've just summarized the result, the first result. Okay. Now we want to show the next result. So it's more that the idea is that it is more than just a D class. Okay. And we'll see. It's obviously we'll see a regular D class, but it's more than that as well. More than a regular D class also. Okay. Yeah. So let's come to the precise thing. So given an L class, so this is an interesting. Given an L class, so given a column, so now it's already a D class. So this confusion is now precise. That is a D class. Given an L class, we want to show that there is an R class such that not the intersection, the product is non-zero. So this is the classes. Okay, these are classes, and yeah, we want to show that the product is non-zero, and that is again simple to check. So if the product is zero, if L times R is if L times R is zero for all R, then basically you can take the union for all R's and overall the R's, and you'll get your, because it's a D class, you can get your semi-group, and then L times S will be zero. But then again, that's not possible, right? So of course, here our standing assumption is that it's not a null semi-group, meaning that S square is not zero, and the multiplication is not null. Okay, and so if that doesn't happen, then again, some small check that, yeah. So yeah, the assumption is that L times R is not zero. So for given any L, there will be some R for which the intersection, not the intersection, I'm sorry, the product L times R, this not R times L. Okay, we're doing L times R. The L class is on the left and the R class is on the right. That thing I think will be important. Yeah. Okay. So again, L times R is an ideal. Now it's a left ideal because you have L on the right to cushion the left element multiplication and R on the right. So L times R will be S. And wait a minute. So L times R is S. Yeah. So let's just run the few steps here and do something interesting. So given this L class, there is an R class where product is S. Okay. Now because the product is S, you can just do some multiplication like this, LR, LR, so is clicking cubes and so on. Then RL times RL is non-zero. Okay. The whole point of this is that the corresponding H class, this corresponding H class will be a group H class. That's what we want to show. Okay. So yeah, so now R times L will be, okay, so let me first say the main thing. The main thing here is that so we want to show that this L and this R, their intersection will be a group H class. Okay, so to show that the intersection is a group H class, you want to show that R intersection L square, right? We want to show that R intersection L is H class. Right? We want to show that the square of this is inside R intersection L. Okay, and that is again a simple check that again one can run and do it. Okay, so I'm just skipping that again. But the point is that whenever you have an L class and an R class, whenever you have an L class, there will be an R class for which the product will be S, and then the corresponding H class will automatically become a group. Okay, so this is the main meat of the matter. This is just small checks one has to do. Yeah, so I have written the proof here, but I think I will skip it because of the time constraints. I have around 100, quite a few more slides to do. Okay, so yeah, I'll just say the final statement. Okay, so we have the following thing. Okay, for every L class there is an R class like this, and whenever for every L class there is an R class for which the intersection is non-empty, the square is non-null, and whenever this point is that whenever the square is non-null, it becomes an H class, which is a group H class, and that's the one possibility. And the other possibility is that it is null. So the whole point is that there is no middle possibility. Okay, because whenever L intersection R square is non-zero, it's always contained in L intersection R. So L intersection R square is always contained in L intersection R in this case, because of the simplicity that was in the small checks. So it's always contained in. So it will either be zero, L intersection R square will either be zero, which means it's a null H class, If it's not a null H class, then it's a group because it's contained in L intersection R. H square is contained in H. So this is really the fantastic point here. Either every H class is either null or it's a subgroup. Okay. So this means that if you have no zero in your semigroup, if it's a completely simple semigroup without zero, then H will be union of its maximal subgroup. So it's a bit, yeah, it's a good thing, union of maximal subgroups. And of course, now if it's commit, it's just a comment. This will not be useful for us. If it's a commutative setting, then obviously the H class is your D class, and so it's a group. It's a commutative group. Okay, so this completely simple semigroups become groups if it's commutative. So this is the interesting thing. Okay, so now we will again want to give some characterization of these things in terms of idempotence. Okay, because eventually the semigroups that we will be looking at, the transformation semigroups, they will be generated by idempotence, and so these properties will be useful. Okay, will be useful. Yeah. And yeah, so obviously now S has idempotence, it has H classes and so on. So S has idempotence and yeah, and every row and that. So those are general things which are always true. So I'm not saying that. Okay, but we want to analyze this. So because, so just share this in short, because one second now. Yeah, because E and F are two idempotents, and because S is just a D class, right? They will be incomparable. So we know this result in general, right? Two idempotents in a D class will be incomparable because I mean the L classes are incomparable and so on. So obviously the H classes. Okay, so when I say comparing idempotents, I mean I mean you give the based on the H classes, right? Because every H class has only one, and so the H order can give you the can give you a partial order, truly partial order on the idempotents. Okay, so that's clear. So every idempotent in a completely simple semigroup is primitive. Okay, but as is usual the case with idempotent if you give an idempotent type property for something, usually the converse also comes out to be true, which we have seen in the course. But here also the converse is true. That is so stated here that if S is a simple semigroup, if S is a simple semigroup, and if S has minimal idempotent, so we just need one minimal idempotent. Okay, so we are starting with the assumption that S is simple semigroup. We'll have to start with that. So we just want to see the distance between simple semigroups and completely simple semigroup. So we have a simple semigroup to start with, and now if it has even one idempotent, which is minimal idempotent, okay, then it is a completely simple semigroup, meaning it has a minimal ideal. And again, it's a easy thing to check. And the key is that what's your natural choice? S times E is your minimal left ideal. Right? S times E is your minimal left ideal. Is that's a claim, and that's a natural claim to make. And then there's small checks that you can do. Okay. So okay. So I have one question. Should I do the details of these proofs or? Hmm, these small results, should I do the details of these or should I move for like leave these details? Oh wait, sir is not there. Hello. Oh, I didn't know that sir is not there. Wait, what should I do? Should I pause? I have to, obviously have to wait for sir, right? Wait, I'll just message him. When did he leave? Does anybody know? I didn't notice. Hello. Oh wait, what's wrong? Oh yeah, yeah, and like why did he? I think connection issue. Very strange. Oh, yeah, I have just mailed him. I don't have any other contact. Uh, okay. And it's not even being recorded. So if he doesn't see it, then that's I won't get the marks. Okay. Right. Okay. So now we have all the properties of completely simple semigroups that we wanted. So in short, they are D classes. Even if they are infinite, they are D classes. They have all the idempotents are primitive, and every H class is either a subgroup or null, meaning that H square will be 0. Okay, so these are the properties. Now we want to come to examples, but these are actually not examples. These will be the way in which we will encounter completely simple semigroups, or rather I should say we'll use completely simple semigroups. So what is the point here is that we start with a D class. Okay, we start with a D class of an arbitrary semigroup. Okay, and we would want to give it the structure of a completely simple semigroups, if completely simple semigroup it's possible. Okay. So we define something called the trace of of a D class of a semigroup, and this is nothing but we just want to give a semigroup structure, a closure structure on it. So on D, you just add a 0, and then you define the multiplication A star B as AB if AB is in D, and otherwise it's 0. Okay. Now, one may notice that for this definition to be non-trivial, D has to be regular. Because if D is not regular, then A times B will never be inside the same D class. So because we know that, we know that if you have A and B, so maybe I can just show it here once again. So we know that if you have this and there is a here and there is a B here, then AB is yeah, AB is there, in RA intersection LB, if and only if there is an idempotent here. This is some result location theorem which we have proved earlier, and it's easy to show. So this will make sense only if, meaning it will be non-trivial only if the D class is regular. Okay. Now it's not a guarantee that if the D class is regular, then for every product AB will be in D. That's not a guarantee, but yeah, at least to start to be non-trivial, we have to, yeah, this has to be true. Okay. So it means that we'll be looking at regular D classes. Okay, and in our in our problem, the transformation semigroups, they are regular D classes. We have enough idempotents. So that's not a problem. So this is the definition. Now we want to show that this is a completely simple semigroup. Okay, completely simple semigroup. But a more natural question to ask is, what are the L classes? And this will actually help us to show that it's a completely simple semigroup. But is, what are the L classes of the trace of D? Okay, so we have this big semigroup, semigroup S, and we have a D class in this, and we are giving a new structure on it, the trace structure. So a lot of elements are getting killed to 0. Okay, A times B, if the product is not in it, is getting killed to 0. So the L classes can potentially change. It means it's not a priori true, but in fact it's true that that they don't change. So the L classes of the trace of D are exactly the L classes of S which are in D. I mean, if it's not in D, then there is no. So so one side is clear that if we have an L class in the trace of D, then that L class will be contained in some L class of the original semigroup. That is clear. But what we want to show is that if L1 is an L class of S, then it's not destroyed, or it's not changed, okay, by using this new structure. So L1 be in L class of S and L1 be in D, we want to show that L1 is an L class in D. So this is different because we want those X and Y's we want those S1s and S2s which relate X and Y to be coming from D itself to make sense. Okay, so let's do the details of this. So X and Y is in L1, which is our L class of S. So X is equal to X1Y and Y is equal to S2X and so on. Now, how are we going to show that X and Y are L related in L1? In D. We are going to use idempotents, and we know that it's a regular D class, so there is an idempotent E there, which I have noted here. So we will show that X is D related to E, and similarly for Y, that will be same. Okay. So again, this is simple. So we have X, and then we have this idempotent. We have the idempotent E here. So we know that somewhere along this row there will be an inverse, some inverse of X, that is X prime, and then we know this, that if X and X prime, if X and X bar are like this, then on the other two vertices there will be an F also. On the other side corner there will be an F, which is also an idempotent. And basically you can use F and E to show that X and E are L related. But what is already clear is that E times X is X. E times X is X, that's clear. So from X you can, so from X you can go to E. From E you can go to X by this. Okay. Now we want to show that for x there will be an S3 for using which you can go to E. Okay. So this is again, you just take this definition of the inverse and you multiply by an x bar, and so we get this. But it's x bar x has to be E, because x bar x has to be inside in the same H class as E. So it has to be E. Only one idempotent is allowed. So it has to be E. And so with x we can multiply something on the left, which you can get E. But this thing is in D, one can easily check, because this is again some sort of an inverse, okay, of x, and we know all the inverses are in the same D class and so on. So again, some small details aside, but this, so we have shown that the L classes remain the same. Now the L classes remain the same, the R classes remain the same, and so the D classes remain the same, and so yeah, so the L classes remain the same is okay, but the D classes also remain the same, which means that it's simple, which means that it's just a block, it's just a D class, so it's simple. To show that it's completely simple, we have to do something else. So that's step 2. Okay. And step 2 is that we want to show that every L class is in fact an ideal, and we know that if it becomes an ideal, then that L class has to be minimal, and so on. And so we just want to show that every L class is an ideal. Okay. And yeah, that this is clear, because I mean, when you go down by the L order, um, one second. So we want to show that it's minimal. Yes, right. So we want to show that it's a left ideal, because if you take an L class, you take an element, you multiply on the left. If it's not in an L class, then it has to go down. But it goes down means it goes outside the D class, which means it's 0, which means it's there in the ideal, because you put the 0 for that. And so every L class is an ideal. So this becomes a completely simple semigroup. In fact, we have shown that every L class is a left ideal. Okay, so every L class is a left ideal. And this is true for 0 completely simple semigroups, right? And so trace is 0 completely simple, right? And but then the issue is that not every time we'll be having L classes. Sometimes we may just have a J class, especially if you are dealing with the case of infinite semigroups, then you may have to start with a J class. Okay. And meaning the J class will be the natural thing to start with, and it means the J class will not be D class, so you may have just a J class. Okay, so we want to show that the principal factor of a okay principal factor I've not defined. So it's basically you have start with the J class, and you do the same thing as you did with the D class. You multiply two elements in the ordinary way if it's there in the J class, and you declare it to be 0 if it's outside. So you just do that. And so this is what is known as the principal factor of the J class. So just a new operation to make the J class a semigroup. Okay. Now this will not be completely simple, and we cannot expect that, because it's an infinite case. The descending chain condition may not be there, but it is simple. Okay. It is simple. Zero simple means if 0 is there, or it's null, which is fine. If J square is 0, then nothing can be done. Okay. So now again, the proof of this, the idea of the proof of this is that the idea of the proof is that you take this entire semigroup and you take the J, and everything below J, you just kill that. So you quotient J by that. You quotient J in the semigroup. Basically, you take J and you take the all the ideals below J, and this becomes an ideal. But then you quotient it by the ideal which is sort of all the J classes just below J. Okay, so that's when you quotient it by that, then the new thing you get is exactly the operation on the principal factor. Because what's the principal factor doing? If A times B is not in J, which means it's below J, then that's 0. So this quotient is exactly the operation on the principal factor. Okay, but when you do the quotient of J by all the J classes below it, which means you're killing away all the possibilities of any other ideal, right? So it cannot have any other non-trivial ideal. So that is again just the idea. And I think I'll skip the proof of this one. It's I think we don't have time. Yeah. So right. So now we come to more concrete business, because this is really what we need for to count and to find rank and so on. We need concrete stuff, right? We want a representation theorem kind of thing. So we'll prove something called a basis theorem for regular D classes. I think this is something which we have done. And yeah, this will be the first step towards a more concrete theorem for completely simple semigroups, which are more than just regular D classes. So what is it? So it's very simple. So you take a G, you take this D class. Now it's certain that you can put the G, and there will be some G, which we know, and there's some G. In fact, in every row and every column. But you can take one G and you can place it in the corner. That shuffling is okay, that you can do, and place it in the corner. And now, one second, some message. Okay, yeah, I think the time is up, right? Yeah, but I'm not done, so I'll just continue. Yeah. Okay. Okay. So we have this. Yeah. So now the claim is that if you take the G and you take one element each from the first row from every H class of the first row. Let's call that Lj, and then one element each from every H class on the first column. Then every Hij can be represented as Ri times G times Lj. And this Ri and Lj could be any elements, just that they have to be one each from every H class. And now, this is again a simple result. Just to use the Green's theorem, from G you come to from this H class, you can come to this H class that contains Ri by multiplication by Lj, and similarly you can go to the right by left multiplication by Ri. So that is simple. So I'm just skipping that. So this is what we have, and this is unique. Again, that can also be checked, and yeah, so it holds for regular D classes. Yeah, so every Hij is this thing. Right. So now every Hij can be expressed. What is where we are going? So we are tending towards writing this D class as just a group and some indices, just a group and indices. Right. That's really generating everything. So that's where we are moving. And yeah, we want to see further ramifications of this for the case of completely simple semigroups. Okay. Yeah. So now that we have a new representation, a basis representation for every element. For every element x and y in the D class, so x will be something like this: Ri times q times Ri times g times q lambda, and similarly y will be Rj times h times q mu, based on the choices of Ris and q lambdas we make. We have x times y, but whenever you introduce a new coordinate system, a new basis system, you would want to know how to multiply elements in that and represent the answer again in that same way, in the same way. Yeah, same terms. Okay, so we can just stick the elements together. Okay, right, but it would be very good if this q lambda times Rj was a group element, right? Because then again, this entire answer would look exactly same, like some indices on the R index on the left, some row, something from some column index on the right, q lambda, and then this entire thing in the middle would become a group element, will become a group element, right? And so we want to show, and this is in fact true in completely simple semigroup, and that's what distinguishes this, makes it more special. So this q lambda times Rj will in fact be in G, and that's again, that follows because L1, that is the first, L1 is the first column, right? L1 is not just a left ideal, but it's a semigroup. Sorry, I'm sorry. It's not an L class, but it's a left ideal. So Rj is in that. So when you multiply by Q lambda, that will also be in L1 because it's an ideal. So again, we see how we are using the property of a completely simple semigroup here, right? So Q lambda times Rj will be in L1, and similarly Q lambda times Rj will be in R1. So it's in G. It's in the intersection. It's in G, and so we can write the multiplication like this. Okay. Right, now we can just write this in a better way. Yeah. So S is a completely simple semigroup, and these are the indices of the rows, and these are the indices for the columns. And when you take two elements and you multiply it, you can write the product like this, but this also belongs to the group. Yeah, other thing is that it may not be in the group, it could be zero also. And ideals have this thing that it could have zero also. Okay, so now we just want to write it properly. So here is what we want to do. We want to take an element Ri Q lambda, and we want to split it into three. There are three pieces of information. Yes, we just split it into three coordinates: Ri comma G comma Q lambda, and then the multiplication becomes like this. But more importantly, S becomes isomorphic to I cross G cross this wedge, new index wedge. Okay. Yeah, union zero. Yeah, zero, you may have to introduce a zero. Yes. Okay, you don't have to introduce a zero, but this will not capture the zero. So you have to introduce a zero for the right side. Right. And now this is taking the shape of a matrix. So if you have a matrix P, if you have a new matrix, different matrix P, okay, which is wedge times I, okay, and if the lambda comma jth entry is q lambda times Rj, then you can just write the product like this. Right? You can write the product like this, p lambda Rj. So now we are coming towards the Rees matrix. We'll see what is exact matrix. Yeah. So S is isomorphic to this. That just follows from the basis theorem, and that the product remains in the S is isomorphic to this, that follows from the basis theorem, and the product also, the middle component still remains in the group. That's a good thing for us. And so we have this matrix which is not I cross wedge. Okay, it's wedge cross I matrix, because you can see it's picking up the second coordinate first and the first coordinate second, and so it will be of this form, right? So now this is how the multiplication is. So it's isomorphic to this matrix. Now let's just study a few properties of it, because not any ordinary matrix. So the matrix, the elements of the matrix are group elements. Okay, just give me 1 second. Yeah. Sorry. Yeah. Right. So the elements of the matrix are group elements, and also, yeah, what is an H class? What is hi? What is hi lambda? Hi lambda will exactly be this: ri comma g comma q lambda. Okay. So when will the multiplication, when will an H class be null? We know that every H class is either null or a group, and we can even see that directly from here, but we're not going to so many details. Hi lambda is null precisely when P lambda j is equal to 0, because P lambda j is 0 means that multiply any two elements, you get a 0 in the middle, which means it's 0. That 0 in the middle, if any element has 0 in the middle, it means that's basically equivalent to the 0 element. Okay, so we have a precise way in which we can spot nulls, and this will be extremely useful for computational questions, which is what we are going to do. Okay, so because S is a completely simple semigroup, every row and every row has a group, every column has a group H class, every row has a group H class, and so P lambda j, this matrix, okay, it may have a lot of zeros, but every column must have at least one non-zero element, and every row must have at least one non-zero elements, and that's the definition of what is known as a regular matrix. Okay, right. So that is a regular matrix, and yeah, so the matrix is regular. Okay, now we also want to understand, just want to see why this is like, okay, like how this is analogous to some other results in algebra, just for 1 second. Okay, so if S is a completely simple semigroup, then we know that S can be written like this. Now the matrix comes in the picture, it's a regular matrix. Okay, now if we want to see everything in terms of matrices, okay, then we can call this element, which is I comma g comma lambda, okay, as we can look at it as a matrix, okay, in which only the I lambda jth entry is G and every other entry is 0. So we can look at it like this. Okay. Now, when you are multiplying two elements, okay, then you're essentially just multiplying the matrices, but just putting a P in between. Okay. So if the matrix for this is A and the matrix for this is B, then the star multiplication is just A times P times B. That is essentially what is happening if you want to look at everything in terms of matrices. But that will not be useful for us too much, because these matrices are just matrices of semigroups, no, not algebra, and we know that matrices will need more things usually, right? But just want to say that this is very analogous to what is known as the Artin-Wedderburn theory in a non-commutative algebra. That is, if you have a simple ring or a simple module, then it's basically isomorphic to an algebra of matrices. That's what the Artin-Wedderburn theorem is. And this is a bit like that. Yeah, but here we need most things to be 0, because we don't want our matrix multiplication to start having addition, because we don't have addition here. Okay, so that's why. So this is the Riesz matrix theorem. And yeah, so we have proved that every completely simple semigroup has this matrix representation. But even the converse is true. Okay, even the converse is true, that every matrix, or every, if you just start with a group G and a matrix P, which is which is a regular matrix, and if you describe the multiplication in the way which we have described, and you start with some indices, so you start with two indices, start with a group G and start with the matrix P, this wedge cross I matrix, and you define the same kind of multiplication, then this will also be 0 completely simple. But this is not useful for us, because we'll only be starting with semigroups and using the matrix representation. The converse is not important for us, but in fact it's also easy to see. And the argument that we will use here will be used later on to prove that it is. Yeah, so first of all, how do we prove that it is simple? So remember, this may not be finite. Just we have represented it as finite, but it may not be a finite D class. So I and this wedge may not be finite things. But first of all, we want to show that S is simple. Okay. Now again, we just start with an element I comma g comma lambda, and this is the kind of argument we'll always be using. Okay, so we start with an element I comma g comma lambda, okay, and we want to say that you can multiply things on the left to get everything. Okay, so obviously this should be lambda. This choice of the last coordinate will be lambda, and the choice of the first coordinate of the left one will be j. That's very clear. Now we'll have to just choose the other things. Okay, how do we choose them? Now we have to choose an I1 and a lambda 1. That's what we have to be careful about. We have to choose an I1 such that P of I1i has to be non-zero. And again, we can do that because in the ith ith column, there will be an I1 which is non-zero, for which Pi1i is non-zero, and we can pick that. And similarly, we can pick a lambda one. And once we do, the product will become like this. Now, star and star two, we can always adjust so this entire thing just becomes an H. So these groups are divisible. We can always inverse whatever we can do, and we can make it H. Okay. So in fact, so we've not proved the converse. We proved that it is simple. Now, proof completely simple. You want to show that every R and L class are ideals, and that's also very simple. If you take an R class, which means what will an R class be? R class will be Ri and everything else in the second and the third coordinate. Now, if you multiply this to the right, this Ri is not going to change. So you're going to remain in that. So this is so every R class is an R ideal, left R right ideal, and so on. And so we are done. So I think we are done with the first part, right? I think done with the first part. So should I stop here? Should I do the second part next day when sir is there, or because I think I've already exceeded the time? Yeah, I think I'll just ask sir to be present, and then I will do the second part. Yeah. Yes. Yeah, I think I'll do that. Yeah. So yeah, because the second part has equally more things. I think I went very slow in the first part. That's why. Yeah, as you can see, this has equally more, but this is more interesting part. Like we'll see the application. Okay, so I think I'll just continue this when sir is there. Okay, so then it's thank you. Okay, so I'm quit leaving the meeting.